Okay, I think we can start. Hi, everybody. I'm Serena, president of the MUNU chapter of IEEE-HKN. We are a student organization recognized worldwide by IEEE as its technical and academic excellence society. And here at Politecnico, we were founded in 2017, and we organize many events, educational events for Politecnico's community. And today's event actually will be presented by our area manager, Sebastiano. He will accompany you through the event and welcome you to today's event. So thank you and enjoy the event.
So, good morning, everyone. I am Sebastiano Guzzone, and I'm the manager of the event area of the MUNU chapter IEEE-HKN. So, today I'm glad to present to you NXP Semiconductors. They will present themselves. There are a lot of groups from Austria, Milan, and all parts of Europe. This event will be divided in two parts. In the first part, we will know something about NXP, an overview about this company, an overview about, in particular, NXP Austria, their research, their thesis proposal, and their internship. After the break, there will be a part about NXP Milan and all the other groups in Europe. Furthermore, there are some of our guests that are alumni from Polito. So everybody, if you have a question, if you are interested in something, maybe their past, don't hesitate, ask them. We are here because you want to know them and they want to know you. It's an exchange, a networking. So I want to thank all the participants today. And first of all, I want to thank Professor Montuschi and Professor Boscolo for helping us with the classroom, because they share with today the classroom. And let's begin with the first group. The first group is the group from NXP Austria. And please give a big applause to Tiberio Fanti and Luca Lingardo from NXP Austria.
Okay. Yeah, thank you very much. So, welcome to this presentation. First of all, I would like to start with myself, in behalf of the company, thanking the students' organization and the department who is hosting us today. So today I'm going to give you quickly, because we are already a bit late, a short introduction to NXP, what we do, where we are, and then an introduction to our site. I'm, let's say, coming from Gratkorn, which is in the outskirts of Graz in Austria, where we have our, let's say, development center. And soon after, Luca, in my group, the technical coordinator, will talk about, let's say, the activities, the academic activities that we are running, and the open position that we have for bachelor's, master's students to carry on the academic activity that we are behind. So let me see if I can progress like this. Yeah. I already spoke about this. So, fundamentally, well, if you want to go deep into the information about NXP, you can find them, let's say, on the web. Shortly, NXP is a Dutch company that was founded as a spin-off of the former Philips Semiconductor in 2006. Today, spread all over the world, and I will show you also, let's say, the countries where we are based, but mainly is a European company. We have more than, let's say, 30,000 employees, and mainly engineers, you can figure it out. And what else? If I can quickly show you, we are organizing mainly in 4 big business lines. So there is one which is focused on advanced analog devices, automotive processing, radio frequency processing devices, and then another big business line, which is the so-called secure connected edge, which has in the belly, let's say, a unit which is developing one of our greatest assets, which are the microprocessors. Our markets, target markets are various, let's say, but mainly you can see it already displayed in, let's say, in this slide. We are covering the automotive market in all aspects, from let's say the dashboard of cars, sensing, controls, and support all the, let's say, the activities which a vehicle takes care. We have another market sector which is the industrial one, so automation of industrial processes. A big one, which is the mobile, where we have different solutions, let's say, for relative to the connectivity of the mobile, or let's say, other features which are today, let's say, completing the functionalities of a mobile set, like file transfer, wireless charging, payments, and so on. There is another market area which is growing more and more every day, is those that one which is focusing on, let's say, the smart home and city. So the facilitation of all, let's say, the application that we have today with the hyperconnectivity and IoT in our houses, or wherever, let's say, we are working and moving around the cities, so accesses, transit, and so on. And then we have one last, let's say, big area connected to the communication infrastructure. So 5G is already a matter of fact, but we are, let's say, working quite, let's say, with a good pace for the deployment of the next generation for the mobile infrastructure. Yeah, these slides show you more or less where we are located. So you can see that the majority of the sites, the development sites, are in Europe, but we have a big part, let's say, connected mainly to the manufacturing, which is in Asia, and a set of other sites which are in the US. The US sites are mainly coming from, let's say, the part of NXP that once was Freescale and Motorola. So focusing mainly, let's say, on the R&D, research and development of microprocessors, and, let's say, ecosystem connected to them. Yeah. In a word, this is the statement of our company purpose, which brings a lot of information together. You can see from let's say, the words that one of the major focus, and we as employees are, let me say, reminded every day, is the purpose is that to really to do our best to develop new solutions which really improve our life. So making it easier and, most of all, safer and secure. Because of this, later during this presentation, we will also have an introduction from one of our colleagues, which is working in the global center, let's say, in Gratkorn, taking care of encryption and security. So, to remark this, this picture very simply explains which are our values companies, in which, let's say, we are also as employees valued regularly, every at least semesters. So there is a lot of focus on the innovations, and we are somehow rated in the way that we approach. So as a single person or teams in introducing, let's say, innovative things to our workflow, if not to our products. The expertise, so the ability to really grow ourselves on the technical side. The collaboration, so the way we interact, let's say, with our colleagues as well as with our customers. The sense of ownership that we show in taking care of our, let's say, tasks or our responsibilities, and the growth that we have to pursue, let's say, in supporting most, let's say, of our activities every day. At the base of everything, in any case, there is trust and respect. And this is an important factor because it's well shown and demonstrated that without this, these values, let's say, on our daily life, let's say, we don't go much further. It's demonstrated that the most returning, let's say, of let me call it aspect of our behaviors every day is, let's say, mainly focused and based on trust and respect. So the way that we interact with our colleagues. Without that one, there is no way to let's say, cooperate effectively, grow, and in the end, let's say, come to products which are satisfying not only our customers, but are also demonstrating to be long-lasting, and solutions which are returning also from the business point of view, let's say. Now, one aspect which is very important, on which NXP is investing a lot internally, if not only, if also externally, is connected to the aspect like let's say the environment and social. Not only, let's say, externally to our, let's say, in respect of with our customers, but also in the way that we approach it on everyday life. Our products are mainly focused today to improve this aspect. So when we say that we introduce new products which are consuming less, they are costing less in terms of manufacturing, we are also aiming or giving our little contribution to, for instance, to sustainable growth, let's say, of our society. So this is very important. And just to give you a confirmation, as many other companies, we are valued or assessed regularly in our performances, and a big chunk of the bonus that we get is based on this aspect, on the achievement of this key performance indicator connected to sustainability. Now, let me shortly give an introduction to our site in Austria. We are based just north of Graz, which is really in the center of the Steiermark or Styria, as you want to call it, in the heart of Austria. Our site was born, let's say, in 1987, if I remember, as a Micron company. Then was, let's say, sold to Philips later on. In 2006, as I said, we changed our skin and became NXP. The site is quite big. We are more or less 800 people, including a number of students that we have on site, around 130, and varies according to the season, because we have also a huge number of students that we take for 7 to 12 weeks during summertime. The average number of students that we have during the year is mainly based off master students, interns, or PhDs. As you can see, we have a huge number of nationalities on site, so much that our, let's say, language for communication is English. And yeah, what else to say? The site is growing. We have just been given, let's say, a new building that we are filling because the plans are limited to, let's say, to extend the number of employees and our, let's say, activities. In terms of, yeah, this is recapping shortly the history of the sites. I don't think I need to go much into these details. So, yeah, in this slide I'm showing more or less how NXP Austria operations are distributed. Beside the bulk, which you can see at the bottom, so taking care of, I don't know, facility, human resources, marketing, and let's say project management, we are based on, or have our business activities on two business lines. So advanced analog for the, let's say, business line automotive, and the so-called secure connected edge. So in Graz we are covering the entire workflow, say from system management, concept development, hardware, software development, or firmware development, test, and validation later on. Besides this, we are also responsible for the customer support, which means that according to the customer, let's say, there are, let's say, we are connected, let's say, around the clock with different sites from NXP or our customers spread around the world. So to provide them support when necessary. What else I can say? Yeah. In terms of, let's say, the business line automotive, in Graz, we are mainly focused on development of solutions for the electrification, which is shared together with the Milan site, so battery management, for instance, and the access, secure access to the vehicle, which means a set of products which are mainly, let's say, focused on, let's say, getting recognized by, let's say, through our mobile or our keys to buy a car, getting access to this, and preventing that the car is accessed, let's say, by thieves. So introducing, let's say, not only the connection, let's say, the RF, but also implementing features to prevent, let's say, stealing the vehicle itself. Yeah, and of course, when we talk about this, let's say, we bring into the picture a number of, let's say, standards that we are developing on site. So, Bluetooth Low Energy, NFC, and the most, let's say, fashionable recent times is the ultra-wideband, which is used for ranging and, let's say, the identification, let's say, of the position and angle of the object that we are looking for. For what concerns the business line, the secure connected edge, instead, we are, let's say, one point is worth to say. Graz has been one of the cities where the RFID technology has been developed over the years. There is not only NXP, there are other companies like Infineon, AMS, so Austrian Microsystem, Renesas, Apple, Toshiba, etc. So it's a cradle of this technology, which has been, let's say, developed over the years in different standards. The Ericsson, the NXP site in Gratkorn has been, let's say, the place where the NFC standard has been developed together with Sony a long time back. Now, let's say, we say that the NFC technology is mostly, let's say, a technology which is mature enough. We are introducing new features, but the future, the outlook is looking elsewhere, mainly on the ultra-wideband. And this is where, let's say, we are mostly focused in, at the moment, let's say, in Graz. Yeah, so I think I can skip this one, it's a short enough time. Yes, on the other side, let's say, beside the ultra-wideband, as I said, a large unit is developing solutions for RFIDs and then NFC. So you can see on the left a number of standards which have been introduced, mainly with, let's say, with the support or the incipit of, let's say, NXP. And you can figure out from this picture that, let's say, this is a pervasive technology that we have all the time, let's say, around us, so for different purposes. So access, payments, identification, many types of identifications, and so on. So anyway, in our site, we are not only developing the hardware, the chips, but we are also developing the firmware, which means, let's say, the customization of the features for our customers, and the support to our customers as well. What else? You will be introduced later a bit better, but say by my colleague Valerio, but Graz is also the global, the site for where the global excellence center for crypto and security is growing. It's a unit which is swallowing everything over time, even our premises, let's say. At the moment is 300 people or a bit more, and is planned to be growing more and more. And here the topics are those typical of, let's say, the security and encryption. So algorithm. So a buzzword can be, I don't know, let's say let's say post-quantum, so encryption. Okay. So yeah, what else? So beside developing, the site is also keeping relations with other industries, making parts, let's say, of clusters or consortia. One of these, the most famous, is Silicon Alpha, which is covering, let's say, Austria, Slovenia, Italy, and Switzerland. We have connections with of course, the major universities of Austria, but we are also, thanks to us, let's say, starting to go beyond the Alps and try to establish connections with others. Not, let's say, the first one, the Politecnico. And beside this, we participated to a number of funding projects which are sponsored and funded by the European Union. And this is the reason why also today we are here, say, and I will give you in short, let's say, an introduction. So just to recap, to give you a picture, the way that we engage with the students are different. So we have usually what are called full-time internships, so working students, which are, let's say, engaged with us while they are students. We're still studying, so based on their availability of time, they carry on, let's say, their studies, and in parallel they work with us. This can be a short-term or a long-term, bachelor and, let's say, master thesis. We have also summer students for a very short time, and PhDs. So there are different flavors for, let's say, and different ways to be engaged with us. We are constantly looking for students from different aspects with different backgrounds, so not necessarily microelectronics. And besides, there are also roles which are not necessarily engineering. So because the students are very often, let's say, also engaged in the support of our, let's say, support functions like business management, quality assessment, project management, and so on, with intention to grow internally, so our future collaborators. Okay, coming to Austria means a lot of things. Very shortly, so there are a lot of benefits connected to the relocation. So there are the support in, let's say, in bureaucracy, languages, courses. We don't speak German, but German can be helpful for some reasons. And then there are, we have a huge, so 800 people means a huge network of groups, of clubs, which are sponsored, let's say, financially by the company in terms of sports activity or social events, etc., etc. So healthcare and, let's say, some health support and so on. What else? I think, so fundamentally the message I want to give is that, yes, we do engineering, we do development, we do a lot of cool things in terms of, let's say, research and development, but our, let's say, campus is a village, and the main task, let's say, is to be somehow to feel each other, let's say, well, together and favor internal movement, let's say, from one area to another, and keep continuously, let's say, in engagement with let's say, universities or other research technology organizations. So I am leading a team in Graz, which is called the CLIF DG team. CLIF stands for contactless interface. So it's a modem. Shortly. So we are framed in our, let's say, business line, which is Secure Connected Edge, and we do develop the digital parts of the modems, the NFC modems, that you can find in let's say, in a huge numbers of more than 80% of the mobiles phones which are manufactured today in the world. The applications are various. So with the chip, let's say, we can turn our mobile into a point of sales for payment, or into a card for let's say, for using the mobile as a card. We can transfer data from one NFC device to another, but we can also use it as a wireless charger. So if you put the earbuds on top of this mobile, you can recharge them in a few seconds. And the same chip is used also in other solutions to get access to secure areas, or to use them, let's say, in passports, etc. Of course, what makes, let's say, the change is the new firmware, which is loaded on top of them. As a team, we are responsible also for the modem, but we have also a number of other IPs. The team is very young, 8 nationalities, less than 30 years, mainly based in Gratkorn, but we have also branches in France. So we have 2 sites in Mougins in Normandy and Sophia Antipolis. Sorry, Caen in Normandy and Sophia Antipoli. But we have also colleagues in Irvine and San Diego and Bangalore, depending on the workload. Yes, as a team, we keep constant connection with the university, and we are running regularly an average of 2 master students per time. So in an approach according to a program where the students are coming one after the other and continue the work done by the other before. Yeah, we cover the lower part of, let's say, the V model of the development, starting from concept, so in MATLAB, Simulink, where we explore, let's say, the architecture and the algorithms. We do then the implementation, verification of, let's say, our code together with firmware, so assembly, integration, and eventually at the end of the manufacturing, we also take the early engineering samples and we run, say, bring up tests on them. So we cover a big part of the entire workflow of the development. This is a simple sketch of our NFC controller. Just to show you quickly, we are responsible for the dark blue parts. So the entire modem, transmission side, receiver side, transceiver, clock recovery, with, let's say, development of in support of the PLL and the DPLL, which are in the analog area. But we also develop other ancillary features like a CLIF, so a coprocessors that I'm going to shortly introduce, and a on-chip scope. The rest of the blocks are developed by different groups which are deployed either in Germany or in France, and they are all assembled, and the back-end design is done in France again. Yeah, so I'm coming now to the reason why we are here today, or where it all started. Tristan project is a project that was has been, let's say, approved by the European Union to support, let's say, development in the range in the area of the RISC-V technology, fostering and trying to develop let's say, an ecosystem, say, based on the RISC-V, which comprises cores, IPs, tools, software, and let's say, giving demonstration of, let's say, this achievement by the European Union. Together with Politecnico di Torino and the University of Graz, we engaged on this project, and with a plan that is going to be lasting over 3 years. This Tristan project is, let's say, made of, let's say, 44 partners over 12 nations and includes the contribution of 10 different universities, out of which we have also Politecnico di Torino and Bologna. It's planned to be finished by the end of next year, so 25. Why NXP is engaged on the RISC-V? As I said, legacy reasons, Motorola and Freescale. We have internal solutions supported by toolchain, compilers, debugger, etc. And we are also member of some, let's say, initiative around the RISC-V. So membership to RISC-V International and, let's say, open hardware. In the future, it's been announced the foundation of a new company, a new joint venture between Bosch, Infineon, and NXP Nordic, etc., which is called Quintauris, which will further invest in the development of, let's say, architecture around the RISC-V. So a big figure around RISC-V. How much time do I have? Sorry? Done. Okay, so I would skip this part if you don't mind, because this is an introduction to the layered approach, and I think Luca will give you more details about the RISC-V, and I think these are slides that can be shared, let's say, later on to you. What I want to say that we, together in the team, together with Luca, we are engaged in Tristan in a task which is called ISA extension. So we are developing extensions, so hardware accelerator, let's say, to the RISC-V for DSP applications. The purpose is to develop, let's say, a new approach in executing, let's say, the decoding algorithms that we are implementing in hardware, making use of RISC-V, of, let's say, firmware, and an external accelerator in hardware. We have already run a couple of round of thesis, and we are looking forward to get new students supporting us in these activities, let's say. So, Luca, I think if the time is short, I can skip this part because it speaks about the contribution of NXP into Tristan, and I think I can make it short. Let me see. Yeah. Maybe it's better that you come here and take it over. Okay? Thanks.
Okay. So, good afternoon, or good evening almost. I'm Luca Lingardo. I am a principal digital design in Tiberius Fanti team, also technical coordinator of the team, and I was, as you, a student of the Politecnico of Turin until not so long ago. I have an experience of 6 years in ASIC development. The first 2 years of my career, I was focusing on space application, safety critical space application, and since I joined NXP 4 years ago now, the main focus is development of mixed signal ASICs for the NFC applications. So what are we discussing today during my part of the presentation for the next 20 minutes, more or less? We will discuss about the Riviera program. The Riviera program is developed under the umbrella of the Tristan activity that Tiberio shortly discussed before. This is a European founded project, so the idea is to improve the RISC-V based ecosystem in Europe in order to achieve independence from UK, from the US, and from China when it comes to development of CPUs. I will discuss about the framework, I will discuss about the problem statement, so why did we start in the first place with Riviera. I will go into high-level technical details on the proposed solution, on what we have done, on what we want to do in the future, how we want to engage with the students for the future developments. So let's start. So the Riviera program. The Riviera program so far has been developed as a joint activity between the Politecnico University of Turin, the Technical University of Graz, and has been coordinated, so the main coordinator is NXP Austria, in particular the Cliff Digi team. Riviera stands for RISC-V ISA extension for RFID application. As I said, the main focus of our team is NFC application, but what is NFC? NFC is nothing but a subset of RFID application. But for the acronym Riviera, we couldn't use NFC, obviously. Let's go to the next slide. So I want to bring you to the problem, let's say, step by step. So I want to start from the origin. What is NFC? What is NFC? How NFC devices are built today? What is the problem about the state of the art? So let's start with the definition of NFC. NFC, as I said, is a subset of radio frequency identification technology, which operates at only one frequency, which is the 13.56 megahertz. So the carrier frequency generated by the device is 13.56 megahertz. NFC devices operate with inductive coupling principle. So you have two devices which are in close proximity to each other that one generate a field, another one modulate the field with inductive coupling modulation. The range is really short, so we're talking about close proximity, otherwise it will not be near field communication. That is the acronym of NFC. And as you probably know, NFC is found in billions of devices today, in multiple IoT devices, for instance, for mobile payment. So when you use your phone to pay, as Tiberio said, you are using an NFC device, but also secure identification at access, also ticketing, also car access, also wireless charging, etc. Who is the authority that regulates the NFC world? It's called NFC Forum. NFC Forum is an association that bundles together different RFID standards under the same umbrella, defines a roadmap for the future of NFC, the use case, but also the quality criteria and certification criteria. In these slides that I guess will be shared with you, I put two links, one to the NFC Forum webpage, and one is a video of what NFC can achieve. So let's go to the state of the art. So this is a simplified architecture of NFC system on chip. So what do we have today? Today we have, so the NFC devices are mixed signal ASIC IC. A mixed signal ASIC is basically an ASIC device where the analog circuitry and the digital circuitry is built on the same silicon. So it's integrated on just one silicon die. What is the problem when we go to the NFC solution is that we have to guarantee high performance and robust communication in different operating conditions, environmental conditions, and as I said before, NFC support multiple standards, so you also have to operate with multiple standards and different communication schemes. What does this mean? This means that we need a considerable amount of analog and digital signal processing to support all the umbrella of communication. As Tiberio said, we developed the NFC digital modem, so our focus is on the NFC digital modem. If we look at the NFC system on chip, we see on the right, sorry, I don't have the pointer, an NFC antenna, which is of chip. Then we have an analog transmitter and an analog receiver. The NFC digital modem is basically the analog to digital interface between the purely analog domain and the purely digital domain. And then we have a main CPU and the memory system that is used to load the main firmware, the software application. Looking at the NFC digital modem, we have the TX part, so the transmission chain that comprises an encoder of the information and the driver of the analog circuitry that then will generate the field and modulate the field for data transmission. When we go on the receiver side, we have custom DSP logic that processes the ADC stream. And once the ADC stream is processed, the data is decoded and then sent to memory for the software application. What is the problem of this solution? Here I try to summarize, but mainly we can say that the problem of this solution is that we have limited flexibility. Once the silicon is out, you have no chances of fixing bugs, or really limited chances with firmware workaround. You have limited possibilities of adding new use cases, and yeah, this is a drawback. Why? Because as I said, you have multiple standards, you have multiple environmental conditions that you have to consider, and on top of that, noise, non-linearities, analog bugs, let's call them like that, are not always easy to emulate or characterize pre-silicon. So what happens in reality is that when the silicon is out, you will see a different behavior, different environment than what you expected in most of the cases. So what do we propose? What do we propose under the umbrella of Riviera? We propose what's called edge computing architecture. An edge computing architecture is an architecture in which the CPU, a dedicated CPU, will be the main unit that will process the ADC data stream coming from the analog domain. Ideally, an edge computer architecture is an architecture that doesn't require any additional support of any additional unit. But for this particular application, we foresee that the microcontroller unit with the dedicated CPU will still communicate with an existing NFC modem. And the reason is that, will be explained better later, but mainly is that replacing completely the custom logic is a really ambitious program that we plan to solve in the future, but this is really, really ambitious for the future. So what do we have? We have the data that will go from the analog front end to the digital front end. They will be processed partially. They will go to the RISC-V base coprocessor unit and processed. Now, what is the difficult thing of this architecture? So NFC operates in real time. There is no post-processing in NFC. So everything has to happen in real time, and the constraints on the time granularity are really tight. So you have to be really strict in the in the time you process the data, etc. Sorry. I wanted to add one thing. So this figure is overall simplified because it can lead to think that there is a direct connection between the existing NFC modem and the CPU. This is obviously not true because the data are first sent to the memory unit, then after being sent to the memory unit are read back by the CPU, processed by the CPU and sent back to memory. So you can imagine that bus congestion, multiple master managers, operating on the memory system can congest the memory, and so respecting the timing constraint becomes really challenging. Nevertheless, again, I made a mistake. Nevertheless, what we think that this architecture will bring in the future is improved system scalability, improved system performance. It's not listed here, but I will also say it will be easier to fix bugs after silicon production, and then improve customer experience. So what we aim to do, what's our goal, is to introduce this edge computer architecture in the future NXP NFC secure controllers and also non-secure controllers. In reality, we already have one implementation of this architecture that has been implemented in 2 of the next NXP NFC controllers. The silicon is out, so we are testing it at the moment. What is the difference between the implementation that we have already done and what we want to do with Riviera? With Riviera, I will show in the next slides, we want to support main NFC applications, use cases. What does it mean? It means full demodulation of the incoming frame. The architecture that we are supporting today instead supports auxiliary DSP applications that will support the main DSP logic, will help to fix bugs on the silicon, etc., but you still don't have full support of the NFC forum use cases and standards. So let's move to Riviera. So Riviera, again, developed under Tristan, under a specific work item in which the requirements is to use a RISC-V based core, which allow for ISA extension, so instruction set extension. So the architecture that we are proposing with Riviera doesn't see a CPU, standalone CPU, but this is a CPU which communicates with the RISC-V DSP coprocessor. This RISC-V DSP coprocessor means nothing but hardware acceleration. So through the ISA extension interface, the CPU can directly communicate with an hardware accelerator, and this hardware accelerator will help supporting the real-time operation that is demanded by the NFC forum, by the NFC use cases. Next slide. But what is the ambition of this activity? The ambition of this activity is written in the third row of the first section. The ambition is to build a proof of concept for an efficient and flexible integrated software-defined radio for mobile and NFC applications. We think that this activity will also pave the road for the adoption of this edge computing architecture for other business lines, like, for instance, automotive with software-defined cars and ultra-wideband. When it comes to the status, the program started in 2022. I will already jump to the next slide. In 2022, we have defined the proof of concept. We have defined the architecture. We have selected the RISC-V core. In 2023, we're starting from the first implementation. We have improved the performance of a factor 15, more or less. This year, we are integrating the Riviera core into an existing edge computing microcontroller unit for NFC application again. And next year, we want to prototype the core on an FPGA platform. So now I go a bit more into the details of what we have done in the past, what we are doing in the future, what we are doing now, what we want to do in the future. So let's start from what we did in 2022. The proof of concept definition, we defined the hardware firmware co-design split. So we selected the core. The core that we have selected is an open hardware CV32E40X core, which was, at least at that time, the only one in the library with ISA extension. We have defined the architecture of the DSP coprocessor. We have implemented the RTL. We have verified it, obviously. We have implemented the C code starting from an existing MATLAB model. We also have a dedicated focus. So here is listed ISO 1443 type A 106 kilobit per second reader mode communication. So this architecture should be able to decode in real time this kind of frame. And we have also defined the performance constraint. So first performance constraint dictated by the NFC forum is real-time operation. Second performance constraint dictated by us is maximum clock frequency 108 microhertz. Why 108 microhertz? NFC operates at 13.56 macrohertz, megahertz, which is, and 108 is a time A 13.56. This is an overview of the core. So as I said, the instruction set extension interface allows the core to communicate directly with the DSP coprocessor, and so this is the enabler to introduce dedicated DSP function for DSP acceleration. Let's go to what we did during the second year. In the second year, we took as a baseline the solution implemented during 2022. We didn't disrupt it, so we didn't modify it too much. But what we did was to identify the bottlenecks of the implemented hardware-software co-design solution and enhance it, implementing dedicated enhancement both in hardware and in firmware. How did we do that? Because it's not trivial. We implemented in-house what we called the coprocessor simulator. Coprocessor simulator was an infrastructure that allowed us to simulate and characterize the performance in an easy way, in an easy and fast way of our architecture. So it was easier to identify the bottleneck, and once we identified the bottleneck, it was easier to fix them. As I said before, the improvement is around 15 times compared to the solution that we implemented in 2022. Here you can see a graph that came at the end of last year. So you can see the performance characterization of the decoding during noise, during data frame, etc. So you can see that for every data bit, we know exactly how much clock cycles it's required to demodulate the data. Here again, an emulation of the performance emulator, let's say. Here we are saying that with X data samplings, of course, X data buffering. Of course, you improve the performance because you buffer the data. You are not so tied in processing all the incoming frames, so you come with an average at the end. Our baseline was 100 data samples, and to reach the 108 megahertz, we need 6,000 data samples to buffer. So let's go to the solution, to what we are doing this year. This year, I already said, we are doing integration of the core. So we are taking the implementation done last year of the Riviera core, and we are integrated it into an existing MCU. Existing MCU means that we already have interrupt controllers, we already have timers, we already have a direct memory access module, etc., etc. Of course, the job is not trivial because you have to implement the glue logic to make sure that everything works together. So it's not trivial neither on the hardware perspective nor on the firmware perspective. The minimum expectation is that we don't have drop of performance compared to what we have emulated 1 year ago. The best case is that we can achieve better performance, obviously. Real quick, because then I have to close, about what we want to do next year. We want to prototype this architecture on an existing FPGA-based emulation platform, which is the CQ Race, that is developed by a third party, but is together with NXP. This platform allows an host computer to communicate with the platform with multiple ports. We are implementing what's in the graph there is called EMU IP, that stands for emulation IP. This emulation IP will allow the host computer to send data to the onboard SRAM, and from the onboard SRAM, sending the data to the Riviera core. Obviously, the data will be an emulation of a real frame, NFC frame. So this was my last slide, and this ends this part of the presentation.
So, if you have any questions about the Riviera program, about NXP Austria, let us know. There are 5 minutes like that. If you have a question, please raise your hand. Okay, so there is a question.
Thank you for the nice presentation. I have a question that Riviera project, is it integrated with Ethernet or InfiniBand or some other kind of technology? Or is it comparable with this existing technology?
So no. In general, the NFC system on chip, we developed the NFC system on chip as a whole. So our team developed the NSC modem. As a group, we developed the NFC system on chip. In general, the NFC system on chip, you have to think it goes into IoT devices. IoT devices have high performance, low power requirements. So in general, the off-chip IOs are SPI, UART, etc. So more or less that's it. Do we have other? Square C, and that's it. SPI, and that's it. So we don't have much more.
For IoT, so in the IoT, the purpose is to limit as much as possible what is called the builder bomb. So whatever you can, even the smallest components on board, or let's call it on board, that you can remove, will determine a huge gain in the margins that the customer has. So in the total cost of manufacturing, not to speak about the quality of cell, because every single component, let's say, brings down the MTBF, let's say, no, or improves, let's say, the possibility that we have issues or shorten the lifetime of the device. So IoT means usually a lot of things. Let's say a board without the quartz, for instance, which is expensive, which is can break very easily. So if you want to go, it means that you don't have to rely on a local clock reference, but you have to recover it from outside, or you have to perform in time enough to before the drift of clock that you have with your own solution, let's say, goes out of range. So this is important. You have to remove capacitors as much as possible. All the solution requires only a battery, okay? And that's it, basically, for the IoT. Of course, if you are on the mobile, it's a different story. Because the system is much more, it's bigger and much more expensive. Anyway, the requirements in terms of quality are much higher. So there, it's another story. But if you think about a watch, ring for payments, let's say we have your chip card, let's say, there is nothing. You have the antenna, okay, and your chip, and nothing more. A passport, same story, another good example, let's say.
Okay, perfect. So now, let's have a break, 5 minutes, and after that we will know something about the group of NXP Milan and other part of Europe. I will ask you to attend the next part because it's really important. There are a lot of teams, there are a lot of research, thesis, and after the event, there will be something about gadgets that I know that you love, so maybe stay here after the break. Thank you. Let's begin with our group from NXP Italy. There will be now a short overview about NXP Italy. So thanks to Massimo.
Thank you. Wow. What have you? So proud to be here today, really. Okay, so this will be very short. I will introduce NXP in Italy and what we do and then I will introduce the next 3 sections. So I will skip this because Tiberio already talked about this. So yeah, we are where we fit. In Italy, we fit the electrification segment of the market. So the leftmost in this flyer. Yeah, let's skip and go to what is NXP in Italy. So we have 2 R&D centers, one in Milan and one in Catania. In Milan, we are about 45 in R&D, and in Catania we are 54 R&D engineers. The Milan site is brand new. We started 2.5 years ago, and we are an excellent center for powertrain and electrification and battery management systems. So in Italy, NXP in Milan hosts 2 business lines, the drivers and energy systems and the advanced power solutions. Inside the drivers and energy systems, we have 2 product lines, the battery management systems, which is about controlling the charge and discharge of batteries in the electrical vehicles. So why is this important? Because there are, typically in an electric vehicle, there are dozens of battery packs. They have differences in their performance from one pack to another. They charge and discharge differently, and they age differently. So what you want to do is to balance the charge and the discharge of these elements, because they are the most valuable parts of an electric vehicle. More than 50% of the value of an electric vehicle is in the batteries, and you want them to to last as much as possible, and to do that safely and reliably, and to understand when it's time to change them and recycle them. So the battery management systems is developing devices to control the monitoring and the charge and discharge of these elements. The powertrain and electrification, which is the product line where I work for. I'm, by the way, a digital verification engineer, and I work on the verification of gate drivers, which are devices that control directly the power delivery to the engines, to the electric engines in electric vehicles. So this is an application which is has safety implications. You know, when you are driving on a highway, high speed, you don't want your devices to break and cause harm to the driver and passengers and people. So this is a function that is safety critical, and it's designed and implemented, conceived, designed and implemented in a way that is driven by functional safety. Then we have the advanced power solutions with two product lines. Power delivery, where you control and the charge of electric vehicles, and system power, where we develop devices to control the power management in embedded systems. So the next three speeches will be about verification, digital verification, and digital design in the power and electrification, and a presentation on advanced power solutions. These are our customers, a short list of our customers. Of course, the market is automotive, but we have also a joint collaboration with the University of Bologna and Ferrari on chemistry of the next generation batteries for high performance vehicles. So we are proud to be partners with Ferrari and Università di Bologna to develop this new generation of batteries. How is life in NXP in Italy and in Milan in particular? So one of the pillars of our being, of our well-being, is doing things together and have fun. And so here is our implementation of having fun and doing team buildings. So we have charity events, soccer, running, skiing, and enjoy time together. And of course, baby soccer with daily tournaments. So to conclude my presentation, NXP is engaged in promoting and developing the STEM disciplines, starting from high school and beyond into university. So we have a program during summer. We have a camp happening in Catania, where students from the high school have spent a full week taking speeches and doing labs and having fun together. And yeah, with no further ado, let's introduce the digital verification in NXP. And I give the mic to Alberto.
Thank you, Massimo.
Così va avanti.
Okay. No. Okay. So, my name is Alberto Allara. I'm a digital verification engineer in NXP. I started to work as a digital verification engineer in SD Microelectronics a long time ago. And before I worked as a digital designer. So the digital verification engineer is not very known role, but it's very important. It is very, it's a role that is very requested in the industry, in the semiconductor industry. And the reason is, I will try to explain briefly. So today, the IC design, the digital one, are basically designed using what they are called hardware description languages. And on the market, there are basically two languages, which the first one is VHDL, the second one is Verilog. Originally, VHDL was more used in Europe, Verilog more in the US. Now I think that things are a little bit changing. In NXP, in our group battery management system, we design digital hardware in Verilog. So if you don't know Verilog, I will advise you to study also this language. So the hardware description languages are basically programming languages dedicated to describe hardware. So they are specialized software programming languages with dedicated feature to basically represent hardware, so represent bit or multi-bit, represent events, timing event, or signal that connect blocks together. They have the possibility to represent an interface like we have in a chip, so a pinout, or a representation of the signal. We need to represent, let's say, concurrency, because the hardware is intrinsically parallel. So those languages allow to describe a thread in parallel. And they represent the hierarchy, because as a good engineering principle, let's say when you design, you need to create a hierarchy in order to cope with the complexity. Okay, so in general, those kind of languages are intended to run they are not compiled in most of the cases, but they run in a virtual environment using a digital simulator. So this digital simulator basically implements a virtual machine with a scheduler that executes the representation of your hardware. And this scheduler basically allows to handle all the concurrency, all the signal, and the execution of your RTL description. Okay. But let's say one of so this is the usage of this kind of language represents an advantage, because it improves the way to represent hardware. But it's also a kind of disadvantages, because in the same way of the software, the hardware description language are affected by bugs. So like we have bugs in software, we have bugs in hardware, functional bugs. Unfortunately, this kind of bugs let's say, are related to hardware representation, a cyclic implementation. So once we have implemented a digital design, this is diffused on a photolithography process and cannot be changed. So any bugs that is present in the implementation it is there. It cannot be changed. If you want to change it, you need to pay a lot of millions of dollars to respin again your process. So basically, all the semiconductor companies, not only NXP, they have equipped themselves with dedicated teams, specialized team of engineers dedicated to simulate this hardware before it is implemented in silicon. And the way it is simulated is basically creating a virtual environment around the hardware in order to test the functionality of the chip before it is manufactured. So the activity of finding bugs, functional bugs, pre-silicon is called verification. So in the software world, it's called testing. In the hardware world, it's called verification. And the verification team are basically borrowing a lot of techniques coming from the software world. So the activity, so we call the verification sign-off the activity of, let's say completely verify and test the functionality of the chip before the tape-out, before the chip is sent to the implementation. Okay. As I said, let's say this technique that we use as a verification engineer comes from the software world, but they are mutated, let's say, adapted to the characteristic of the hardware. So in the software world, it is, in a sense, it is easier because you have only one thread. In the hardware, as I said, everything is parallel, so you have multiple threads, and so it's a little bit more complicated to verify the hardware. In the same way, in the software, we use object-oriented languages. In particular, we use System Verilog. That is a language that is called HVL, so hardware verification language. It's a specialized language for the verification. This kind of languages typically use high-level data structure or software mechanism like, I don't know, semaphore in order to manage the shared resources between the environment and between the component of the environment, mechanism to parallelize process, the fork join, for instance. High-level data structures that are used in scoreboarding mechanism like a queue or dynamic array or associative array, things like that. Okay, so System Verilog, the System Verilog by itself include a garbage collector. So when you generate data, packets of data that are exchanged between components inside the environment, those data are created but the environment, we don't care about the destruction of those objects. Like in Java, there is a garbage collector that manages this information. We use a design pattern, so the environment, the framework that we use, the one that is used in the industry is known as a UVM, Universal Verification Methodology. It's a set of object-oriented classes and a methodology that allow to simplify the implementation of the verification and the implementation of the verification environment. And those framework use a lot of design pattern, like the factory mechanisms, a design pattern that allow to create an object or to replace an object with specialization without changing everything. We use mechanism called constraint programming in order to generate the data. The constraint programming are basically software engineering technique in order to define constraint in a declarative way and avoid to, let's say, let the computer to solve a particular problem. In our case, we define the constraint between the relationship between data, and we let the computer to generate those data. This allows to generate tons of data and to hit corner cases that probably a verification engineer doesn't even think to implement it. We use technique like design by contract. In the software world, design by contract means implementing assertion. But since we are in a single thread environment, the assertion are just simply, let's say, a verification of a condition at the beginning, let's say, before to enter into a function or after exiting from the function. In the hardware world, the assertions are derived from temporal logic, so they are very complex and can be, let's say, the constraint and the relationship between signal, it is verified across different cycles. Typically, let's say, if you have a timing diagram, in most of the cases, it is easier to implement an assertion based on the timing diagram. So languages that are used for the assertion are what is called SVA, System Verilog Assertion, which is a subset of the System Verilog. Since we generate data randomly, we need to measure, to make sure to measure what we have covered. So in the software world, the coverage, it's a technique, the code coverage is a technique in order to make sure that you stimulate your piece of software. So in the software world, it's, let's say, the block and expression coverage, which is part of the code coverage. In the hardware world, beside this metric that are present, there are other coverage metrics like FSM coverage. So we need to make sure that the state and the arc of the final state machine present in the design are covered. Or toggle coverage. So we need to make sure that for a block, all the signal are toggling from 1 to 0 and from 0 to 1. Or functional coverage. So the functionality, the value that we randomize, typically the value of the register or other parameters are covered into, are represented with what is called a set cover point. They are analyzed and covered like, let's say, implementing a kind of histogram. Okay, so all those techniques are used to make sure that to answer one question, that is when we can stop to do the verification, when it is safe to stop to verify the chip. Finally, there are techniques used, what they are called formal methods. So the assertion that are used in the design by contract can be used as a property to verify statically a certain behavior. So in this case, the design, the piece of RTL, does not require a test bench to generate the data, but the tool called model checker are used to prove mathematically that a certain property holds. Okay, so this is typically used for internal block, control-oriented block, because for data-oriented, the size of the internal representation may explode, and so it is suitable for only for for small block, but this is a technique that is widely used in the industry. So I will conclude my description of the activity of the functional verification with this V model. You have already seen another representation. This is used in the automotive industry to, let's say, on one side, to say that for every representation of every requirement, we need to have a connection with this sub-representation. So if we have a set of requirements for the system, those requirements are then exploded in a set of components, and the set of components in the set of block level and so on. In parallel to this kind of implementation done from the architect and from the designer, there is an activity done from the verification engineer that need to implement the verification environment and starting from the day zero. It's basically the verification engineer starts immediately when the designer starts, because he needs to create the environment in order to verify the functionality and the requirement at the different levels. So, and we have mechanisms in order to track, to keep track of the relationship between one requirement and the associated functionality that is, or the associated test or assertion that is used to cover that functionality. So if you see at each level, we need to, the verification engineer need to make sure that the particular requirements are old. So thank you.
Okay. So, la parte digitale, questa qua. Perfect. So, hi everybody. My name is Yuri Giovannone, and I'm a digital designer in NXP, and I'm working in automotive R&D group. I have a lot of experience in this kind of field, because also in my previous company I was involved in such products, and I was working also in technology R&D. So the point for me that at the beginning, when I finished my study and I started to work, was okay, so let's think about what we want to do, so analog or digital. And the point here is that at the beginning I was thinking that there was a really big difference between analog and digital, so a kind of a black and white. So analog should take time to understand about the current, about high voltage, stuff like that, and digital just working on data processing or something like that. But then I started to work in a product that was the power management and power conversion device, and I was a digital guy. So why is needed digital design in a power management system or a power conversion device? So there are a lot of benefits, keeping in mind that this kind of solution can, for example, have more efficiency, because we can, for example, with a digital approach, we can understand better the kind of load the device needs to work on. And working with some information, we can decide to change on the fly some configuration of the device itself. Then, for example, we have the possibility to have more flexibility, but not only for the working on the fly, but also for the tuning, or also to have just one devices that have just one schematic and some characteristic, but each customer can change just writing correct register, the functionality of the device itself. Then we have a better integration with the whole system, because the digital function in a power device can have the possibility to have a better interaction between the microcontroller, and we can have an intelligent approach with the fault protection. So let's think about, okay, we are the best in class of a designer, so we did a lot of really good job, and it's working fine, our product, but sometimes happen that this is not true. So maybe we have some fault, and what we have to do with some fault. If we have a digital implementation, we can recognize the kind of fault and makes some activation for the circuit that protect the load itself, or maybe just speak with the microcontroller and ask them what we should make as action with this fault. Of course, with the analog approach, all this stuff are not possible. With an analog approach, we just have to switch off, or maybe switch off the functionality, or switch off the device. Of course, there is pro and versus about digital approach and analog approach. I'm a digital guy, so I will speak always nice things about the digital stuff. So the last point is the possibility to go earlier in the market. So it's really quite common that when we have a great opportunity with a new market, such as the electrification of the car, the customer also doesn't know really well what is needed for have a nice system. So the flexibility that can be done with a digital approach is fundamental to go to the market earlier to the competitor, but also to give the possibility to the customer to have a reduction of the BOM. Just think about an easy filter, okay? If you know which kind of filter you want to implement, it's quite easy. You can put a RC filter, and then you have a BOM, and you device with this RC filter, and that's all. But if you don't know which kind of filter you have to implement, why don't put the filter in a digital world with just a counter or something like that? So hopefully now you know why it's important digital design inside the power management and power conversion device. Yes. Here I just want to show you some example, and this kind of device are developed also in our group in Milan. I will start with the switched mode power supply. That's a great example of why it's important to have at least the possibility to have a digital control. So let's think about DC or DC-DC converter, for example, a buck boost, or a flyback. All this kind of converter need a control technique. There are several kinds of control techniques, and this kind of techniques can be implemented with an analog approach or digital approach. In this slide, you can see the two possibilities of PI control. You can do it by analog solution, just a matter of deciding which kind of resistance or capacitor to put in your circuit, in your BOM, and that's all. Or you can implement the PI just with in a digital way. And why is so nice to have the digital approach? Because if you want to change the parameter of this PI, just to have to change some value in the register. And if you follow the analog approach, that it's working fine. But if you need to change the function, you have to change the BOM. Okay, second example, we just moving on a different field, so the electrification, where I'm working on. Easy slide, just to understand, we are talking about stuff that go inside the electrical car, nothing more of this. And we are talking about gate driver. Okay, so let's now think what a gate driver is. okay? We have this black box, okay? An input of this black box that we call it gate driver is just on-off, okay? And this is the command that comes from a microcontroller. Then the gate driver speak with the microcontroller and decide to switch on or off the power stage. Could be IGBT, could be SiC, could be something like, you have just to think about it's a kind of power stage that allowed the current go to the load with, for example, a PWM modulation. Okay, so quite easy function, right? Do you think we need logic inside this block? Yes, okay. And do you have an idea how many kilogates, for example, you have to put for all the function that is present in a common gate driver? Okay, it's something like 50 kilogates, okay? It's not so much, but also quite important number if you are thinking that the function of this black box is just to understand what the micro want the power stage on or when the micro want the power stage off. So 50 kilo gates that is used for all the reconfiguration of the device, but also because we are working on a really particular environment that is the car. And in the car, we have to protect the micro that it's working with a low voltage, with the power stage that is working with a really high voltage, very noisy and stuff like that. So all these kind of device need galvanic isolation. In order to obtain this galvanic isolation, typically, for example, for our product, we have an approach that is like that. We have two different devices, two different die, okay, that are present in our device. One device is speaking with the micro, and the other one is speaking with the power stage. They communicate each other with, in this case, with some coils, okay, so wireless communication. And in order to perform this kind of communication, we need a logic that can understand, for example, when the power stage should be on or off, but also that manage all the faults that can be present in the power stage. Okay. So last example is the battery management system. I don't want to spend too much time in order to go in detail with this product because, first of all, it's Monday, and I think it's quite late. So just to tell you that battery management system is another kind of product that are developed in Milan site, and actually with collaboration also with some teams present in NXP Europe or US also. And the main goal is to have a safety function, the performance of the battery in charging, and also manage the multi-cell function, because as you know, when you have a battery and we have more cells, we have to be careful that all the cells will be loaded and downloaded with the correct range, otherwise we will have some problem. I think that I was fast enough, really good. If you want to go in detail with the topics that I just shared to you, please contact me. I'm here, and thanks for the attention.
Okay, so hello everyone. I'm glad to be here. I'm a former Politecnico di Torino student, so back after 13 years, so it's been a long time. So today I'm going to present very quickly, 10 minutes, what is APS. So APS is a division that is, let's say, in our site in Milan, and stands for Advanced Power Systems. So okay, maybe. Okay, it's working. So this division is literally spread around the globe. So there are several sites. You can see sites in US, several sites in Europe, Asia, and so on. And in Italy, we are in 2 locations, one in Catania and one in Milan. And the feature, or let's say challenge of, let's say, this is that, let's say, everyone has his own, let's say, product line, but we have to, let's say, to collaborate each other, which is a real challenge, sometimes also a problem, but something for sure quite interesting. So, as I said, advanced power system means that we are developing power management devices that are quite complex. So we are trying to put some complexity into our products. So I try to, let's say, to stimulate, there is little time, so try to put in a couple of slides, let's say, a couple of examples of what we are developing in Milan and also partially in Catania. So the first kind of devices are, let's say, PMICs or PMICs. So basically, these kind of devices are pretty complex devices which we are trying to provide to a microcontroller a complete power supply network. Not only to the microcontroller, but also to everything that is around the microcontroller. So I try to put in this slide an example, and you can see that this kind of devices includes several regulators, so DC-DC power converters, linear regulators, but not only this, there is a lot of diagnostics, there are some ADCs, there are some any kind of monitoring inside. And of course, in order to make everything interact each other properly, let's say a lot of digital, let's say, intelligence is needed to make everything working. So let's say most of the job is, let's say, analog to develop each IP, each module, but at the same time to make everything interact each other and also interact with the microcontroller, you actually need a lot of digital intelligence. In Milan, we are hosting in some way the R&D part and let's say all the engineering part, because also to validate, to test, and to make this kind of products in production is something pretty complex. So all the engineering part is spread around the world, US, Toulouse in France, and other locations. So this is making this kind of job, let's say, interesting and also challenging. Okay, the second kind of product, and actually we have the expertise and also the ownership in Milan, is a pretty new topic, which is onboard charging. And also Catania site is collaborating with us for this kind of topic. So basically, if you have an electric vehicle, if you can afford an electric vehicle, which is a different story, actually you need to charge it. You would like to charge it from your domestic network or from an industrial network. So basically you need this, let's say, red component, which is called onboard charging. that today is something that is weighing tens of kilos, needs, let's say, liquid cooling. So it's something very big, and it's also very, very expensive. Basically, the purpose is to charge the EV battery, which is a high voltage battery, directly from for instance, your domestic network. So you need to handle very high voltages, powers which are above 10 kilowatts, can be 22 kilowatts, so extremely huge amount of power. And the purpose, or let's say the challenge, is to increase as much as possible power efficiency of this system, to trying to make, let's say, to get rid of the power dissipation in a better way, and also to make these kind of systems as much compact as possible. So in order to do this, all these of course is just, let's say, a high-level, block-level example. You need to integrate all these functions as much as possible. Currently, an onboard charging is made via several discrete devices that are trying to work together. And the challenge, and it's also pretty new, is trying to make modules that could, let's say, trying to integrate as much as possible into some system on chips that can, let's say, interact with the environment. Of course, these are not standard topologies, so each module is a product, and it has several challenges, and control techniques pretty, let's say, complex are needed. They could be implemented in digital or still in analog. And okay, so there are several challenging points that belong to this kind of applications. So I don't want to take too much time on this. It was just to provide you a couple of examples to, let's say, to stimulate your curiosity. Just to let you know that this kind of, the R&D part is really needs several functions that have to collaborate each other. So there are architects, analog and digital architects that, let's say, whom purpose is, let's say, to define the high-level system. There is analog design and digital design that, let's say, as Yuri was saying, they are, let's say, sometimes interleaved. And a lot of verification, analog, mixed signal, and digital. And just to think that this kind of devices, you can have a team which is from 10 to 50 people trying to work together to make it work. And sometimes it happens. So I put some names, so if someone is interested in this kind of topics, just contact us, and okay, we will try to, in some way, to address your needs or your curiosity on this kind of topics, let's say. So that's all.
Okay. Hi. Happy to be here. And yeah, if you are not still completely bored, I will complete the job. And so I'm here to speak about the Competence Center for Crypto and Security. Here you see I am Valerio Costantini, and I am a senior systems security architect. And I'm going to show you what we do in our department. Well, first, you heard my other colleagues speaking about the PL, the product line, or the business line, and I'm not in a product line. What we do at the Competence Center for Crypto and Security is that we collaborate with a product line and with a business line to design their products. And we make sure that the product is designed following all the best practices that incorporates the security by design approach. All in all, we are 300 people. And also in this case, my colleague spoke about they are concentrated in some place, some country, but as a matter of fact, are the Competence Center for Crypto and Security. We are completely spread almost all over the world, but mainly in Europe, because we are a European company. Like to have an idea, I work in Graz, so the same site as Tiberio and Luca. My manager is in Belgium, and his manager is in Hamburg, in Germany. And my other teammates are spread here and there in Europe, in France, in Germany, other sites of Germany, Belgium as well. We also have people in the US. Here we see more or less what we do in our site. So we may collapse all our activities in these three main blocks. So we have technology. Technology is about designing IPs. The IP is an intellectual property or a subsystem. So this might be a security subsystem, like a crypto coprocessor. It could be a hardware sensor, like to detect some hardware attack, or even software libraries, like the cryptographic library implementing some cryptographic algorithm. So you may know AES, RSA, ECC, all of those. We will also see, it's in the next slide, we're also quite proud that we actively participated on the new standards for the post-quantum cryptography. NXP co-authored the proposal for Kyber. Kyber is the key encryption mechanism for the post-quantum cryptography. So besides technology, we also have processes. So in processes, we have the security product engineering process. Here you see SMP, that stands for Security Maturity Process. And that's more or less what the framework into which me as a system security architect work. So this means that as a system security architect, for example, I get the requirement. They may come from the market. They may come from a specific customer. Usually they also come from some standard. So for example, you heard the colleague speaking about ultra-wideband or an also automotive. And for example, I work on the ultra-wideband module that we plan to integrate into vehicles. So in that case, I had to take into account the ultra-wideband standard because some cryptographic features are requested. But also, for example, you may know about the ISO 21434 that describes the engineering process for an automotive the security by design for an automotive system for a vehicle. In our department, we also have expert for the you see the third part certifications. These are external bodies, so mainly certification labs that provides the certificate for the security certification of a certain product. So you see here CC, that stands for Common Criteria. That is the most one of the most important security certification, at least in Europe. You may know that many public agencies buy their products based on this certification. Common criteria is not only about embedded, it's all about any kind of ICT system. But obviously, if you want to have a whole system that is certified, you also need the microprocessor that may need to be certified. This goes into more details about the certification, but if you want to have also, for example, hardware security, also the microprocessor needs to be certified, and so this goes to NXP. We have EMV core. You see this is for payment. So for example, when you use your smartphone for payment, that's also been mentioned by my colleagues. In there, you have a secure element, and that secure element is expected to be certified according to these standards for allowing the payment. You see also here we have CESIP. CESIP is another certification framework. It's based on common criteria, but I mean, this is going to be very boring. And then we have the Product Security Incident Response Team. You see here the piece here. This is our contact point from where external stakeholders may contact us in case that they might have they may have found some vulnerability, for example. This usually happens via researchers, and they want to have a responsible disclosure, so they want to contact us to say, hey, I found this weakness in your product. So and so maybe they may also want to suggest some mitigation or also showing what they found. And so this is the way how they can do, and so there will be an interaction, and the issue will be, the finding will be solved. Obviously, you see also people, because security, as a security architect, I am mainly responsible for that in the product, but I'm not the only person that can do that job, because there might be also the integrations of our subsystems might be an issue. May reveal some issue. And so also the other colleagues may to be aware about what security is, just to be aware, so that the security architect can take ownership of whatever may come in. And this also goes into the security awareness of the organization. And okay, yeah, this is what I mentioned before. Probably you know about the quantum computer, and you may also know about the challenge that the quantum computer poses on the point of view of cryptography. Because we know since the 90s, RSA, ECC, all these asymmetric cryptographic algorithms are weak against quantum computers. And so NIST started a challenge to find new algorithm to replace the RSA and ECC that are currently in use and still approved, but to prepare for the incoming era of the quantum computer. And as I said here, also NXP participated and filled a proposal for some cryptographic algorithm. And in the meantime, we are also we are starting to integrate these post-quantum algorithms as they are more and more requested because of regulations, also because of our customers willing to have some differentiating factors in their product, and so we need to support from the hardware. Here you see these are all our sites. So you see there's a lot of dots in Europe. We have a couple of sites in France. So we are in Toulouse and I think Sophia Antipolis. We are in Graz, so in Austria, in Hamburg, in Glasgow, and yeah, then there's also colleagues in India, China, and the US. So that's what I said. We are not really focused on just one country, and also myself, I mostly do not work with colleagues in Graz, because many of my colleagues working in my same projects are either in my specific case, it's India and France, for example. Here we see, well, these are the different fields that the different sub-teams. So here we see the security concept. Here you see, so I'm mentioning about the post-quantum cryptography. It is, then we have the security architecture, that's where I work in. So how to make possible how to integrate PQC on our product, for example. Then we have the security IP implementation, so how to implement that, for example, PQC, that algorithm in our hardware or software. The vulnerability analysis, that is either testing, I mean, what do you call testing usually on security? We say vulnerability analysis, penetration testing, and it is the way how we verify that the countermeasures that have been designed by the architect have been actually properly implemented and mitigated the risk as it was expected. Obviously, it's always about mitigating the risk. You cannot reduce the risk. That's never the absolute security. You can never have a non-hackable system. That's absolutely impossible. But with vulnerability analysis, we make sure that this risk is as low as possible. Then we have the security certification. That's what I said before. This is usually goes via some external lab. So it's not a thing that we say by ourselves, but it's always someone else checking. So they also repeat penetration testing on their side to verify that everything was as it was expected. In that case, it also goes to some framework that is defining the standard so that either the manufacturer, so we, and the certification lab can agree on how to test the thing, and that makes sure the certification is actually implemented. Then we have R&D, basically identifying and addressing future market trends and needs, and also potential disruptions. And in the end, well, also standardizations. This is a thing, as I said before. Here we have, also Tiberio said at the very beginning, we are a growing department. This is also because the standardizations and all the scenario around us is growing more and more. If you think in the last years, for the automotive, they issued the ISO SAE 21434. In the industrial, we have the IEC ISO 62443. Then we have for payments and other standards and so on and so forth. So, and the thing is not stopping. I mean, we also have in Europe the NIS directive, something similar in the US, and so on. So we always need more and more people also to stay ahead. The product security incident team, well, as I said, this is mostly for when we have an incident, so somebody wants to responsibly disclose a vulnerability. And then, yeah, here we have my, I think, last slide about the vulnerability analysis lab. This is how we test internally, so how we do our penetration testing in-house. So you see that here we have a lot of robotic systems. So for example, if you, okay, I cannot see. Is this working? Laser? Yeah. Here you see this is a robotic system where on the base you have an IC, and this robot is used to properly place the probe to inject an electromagnetic field into the device to see how the fault is injected and eventually handled, for example. You see here, this is very much the same, I think, or it's a, no, sorry. This one here is the EMFI, so electromagnetic field injection, and here you have a laser, for example. So all of these things are tested. Obviously, you have a robot because the geometry where you spot may be a thing, and this enhance the precision. And well, I hope I've been on my time, hopefully. And other 2 minutes. Well, let's see what we do. Well, for example, I may describe what I do. Maybe you might be interested, I hope. As I said, I'm working on the UWB module. This ultra-wideband system is basically used for the digital key. So it means that you may have, for example, your smartphone acting like a digital key for your car. And in that case, it means that you have your, for example, your smartphone sending some UWB frame to the receiver that is in the car. And then the car, based on will measure the distance and would say, okay, we are inside, the smartphone is within some centimeter or meters. I actually do not know because this is implementation specific. So one customer may say, this is the distance. Another customer may say, this is our distance. So it's really implementation specific. But then, what's the challenge here? The challenge here is, for example, that when you try to range two devices that are for example, UWB, usually you use 10 meters for an ideal ranging. It may even work within 100, but you don't have a very high precision in that case. And so in that case, you want a very precise measuring. And this is also the reason why you use ultra-wideband, because it allows you to have a centimeter level precision. And at the same time, you may have some attacker that may try to, for example, maybe you saw on the web that have been some thief trying to enter a car where the car was, for example, parked on the street, and then they kind of relayed the signal to open the car. In that case, because very likely the car, I know as you because it was on YouTube, but very likely it was because the ranging in that case was based on BLE. Maybe you know BLE because it was also used a couple of years ago to do contact tracing for app during the pandemic. And in that case, how does the ranging works? In that case, you use the RSSI signal. So you actually measure the power at which you receive the signal. You assume to know what was the power that at which it was sent, and then you derive you calculate the degradation that you have over the year, and then you measure the distance. Obviously, these things can be misused by an attacker because they may relay the BLE signal, the Bluetooth signal. So this is the reason why, for example, in modern cars they are integrating UWB, so ultra-wideband. In that case, it works with a time of flight. So it means that first you have a device sending a pole message, and then with some ranging marker. And then the other device measures the ranging marker at transmission of the other device, and then compare with the R marker, so the ranging marker at the reception of the frame. And then you measure, it's a bit more complicated than that, but this is the idea. And then you measure the time of flight. And by measuring the time of flight, obviously it's an electromagnetic signal, so you know it's spread at the speed of light, and then you get the distance. And obviously this cannot be relayed in the same way as a Bluetooth signal, for example, when you use Bluetooth for ranging. But in literature, there's also very known attacks to inject some peaks to fake proximity. And the biggest challenge in security, for example, on UWB, is to detect this fake peak to avoid this distance reduction, but at the same time allowing a proper usage of the product, because usually there's also the other challenge that we have on security. If you make the more you make the product secure, and probably the less it will be sometimes also usable, because maybe you may reduce the tolerance, and if you reduce the tolerance, then you fall in in cases where the device is not properly working. So this is always about balancing, and now we are.
Okay, so thanks for all our guests. And just a few last words before the end of the event. Our association organizes many events of this kind. There are general topics and more specific topics, like that, for example. And for those who want to become a member of our chapter, the next recruitment will also take place in October. To thank you for your feedback, at the end of the form you will find a link to the slide used today. I don't know if... Okay, perfect. There are two QR codes, one with the thesis, proposal, and internship by NXP, and the other one with a survey and for your feedback. At the end of this event survey, you will find the slides that they were used today into the event. Furthermore, we still have 10 minutes, so you can come here and do networking with our guests from NXP, talk with them, share maybe your opinion and your CV, for example. And that's all. I also thank the online audience, and thank you all, and see you at the next event.